Alright, so yesterday we talked about the electron affinity, and so now we're going to pick up on number 4, ionic radii. Okay, we're almost done, people. We can applaud ourselves for making it through this. Okay, so before we start talking about ionic radii, you have to know the difference between a cation and an anion. A cation is a positive ion, which means it has done what with electrons? Lost them, right? Okay, so this means we have lost electrons. Okay, anions are negative, which means they have gained electrons. Okay, now you got to know that. If you don't understand that, then you're not going to be able to understand the trend. Okay, and this isn't really a trend. This just honestly makes sense. So if I compare a positive ion to when it's in the neutral state, what should happen to the nucleus of the positive ion? Okay. It should shrink. It should actually get smaller. Why? Let's look at lithium. How many protons does lithium have? How many protons does lithium have? 3, because it's number what on the periodic table? 3. Okay. So this lithium has 3 protons, and this lithium has 3 protons. Because remember, the number of protons is what makes it that element. Okay, you can't change the number of protons without changing the element. So this has 3 protons, and this has 3 protons. In a neutral atom, the number of electrons is the what? Same as the number of protons. So this lithium has 3 electrons. This one is positive, so what did it do? It lost an electron, so this one only has 2. So my positive force is greater than my negative force, so those electrons are going to do what? Move in closer to the nucleus. Do we see that? Make sense? All right. Now, what if I compare a negative electron to the neutral one? So let's look at fluorine. Okay. How many protons does fluorine have? 9. All right, so they both have 9 protons, because remember, you can't change the number of protons without changing the element. So that means a neutral atom of fluorine also has 9 electrons. Now this fluorine is a -1, so that means it did what? It added an electron, so it has 10. So what's going to happen to the radius of my negative fluorine? It's going to get bigger. So it's going to be bigger than the neutral atom because my negative has become greater than my positive, so it's going to make my nucleus expand. Does that make sense?
So the negative ones are bigger and the positive ones are smaller?
Yes. Yes, always. The positive ones are smaller than their neutral atom, and the negative ones are larger than the neutral atom. Okay?
I copied like them, you just made you 10 of those too. Just
Okay. Thank you. Appreciate it. All right. So what if they are isoelectronic, which just means ions containing the same number of electrons? Okay. And so what we're going to look at is we're going to look at oxide versus fluoride. Now remember, when we change the ending to "ide," that just means they've become what? It just means they've become ions. They have a charge. Okay? So, oxide, what's the most common oxidation state of oxygen? 2 negative. What's the most common oxidation state of fluorine? -1. Okay. All right, so how many protons does oxygen have? 8, because it's number 8 on the periodic table. So it has 8 protons. Okay? Since this is 2 negative, how many electrons does O2 negative have? It's got an extra 2.
10.
So it's got 10. Okay? Well, let's look at fluorine. How many protons does fluorine have? 9. Okay, it's F negative, so how many electrons does it have? 10. 10 electrons. So now, which one of these is going to be smaller?
It's going to be F. No, yes, It's gonna be F.
There you go. It's going to be F. F is going to be smaller than oxygen because fluorine has a greater positive pull on these 10 electrons compared to oxygen. Does that make sense? Okay. Same number of electrons, so whichever one has the more positive nucleus is the one who's going to be smaller. We see that? Yes? We're not confused by this? No. Excellent. All right. So let's move on to number 5. Now, 5 is very important that you understand for the next unit. Okay, we're going to start talking about bonding, our favorite. Yay! Covalent and ionic and metallic. We get excited. Or not. It's okay. All right. Well, I'm going to get excited. All right. So, electronegativity is the ability of an atom when it's in a molecule, which means it's participating in a bond, okay, to attract shared electrons to itself. Okay? So you think of it as the atoms in a molecule are in a tug of war. Okay? The most electronegative tugs more electrons towards itself. So the least electronegative is left with less of the shared electrons. Okay? So even though we're sharing them, okay, that means one atom is going to pull more of those shared electrons towards itself. That's why we talk about water being a polar molecule. Okay? Right? Because if we look on the periodic table, we notice the electronegativity of oxygen is what? 3.5. This is in your notes, not on the actual periodic table. Okay? The electronegativity of hydrogen is 2.1. So since oxygen is more electronegative, these electrons that it's sharing here with hydrogen, it's pulling them more towards itself. Okay? That's why we say oxygen has a slight 2 negative charge. Remember, this symbol here just means slight. It means it's not a definite charge. It's a slight charge. And this hydrogen is slightly positive, and this hydrogen is slightly positive. We remember that from last year? Yeah? Okay, so electronegativity is just the ability for something to pull more electrons to itself. Okay? So, as I go across the periodic table, what happens to my effective nuclear charge? It increases, which means my nucleus becomes more positive, which means my electrons become more attracted to the nucleus, which means my electronegativity is going to increase. Okay? I'm going to have these atoms, as we go across, they're going to have a greater ability to pull those electrons into itself when it's in a bond. Does that make sense? Okay? As I go down the periodic table, okay, I'm adding what? I'm adding energy levels, which is adding distance. Okay? So that means, there you go. I'm decreasing my attraction between my electrons and my protons in the nucleus. Okay? Which means what's happening to my electronegativity? My electronegativity decreases. Can you hear me say that out loud, Olivia?
Yeah, I can't read on the page.
So I'm adding energy levels. Let me see if I can write it in different colors. So we're adding energy levels. That didn't help. Okay?
Not at all.
All right. Which means that we're increasing distance. That's what I wrote there. Which means we're decreasing the attraction between electrons and the nucleus. Which means my electronegativity is going to decrease. They're not going to have an ability to pull electrons towards themselves in a bond. Okay, no problem. So if I look at the periodic table, who is the most electronegative? Fluorine. And who's the least? Francium. So when you're talking about electronegativity, because this is going to be important for you to do when we go bonding, we always draw an arrow diagonal. Okay? So that's how my electronegativity increases. So So it's the least down here at the bottom, and it's the most over here at the side. Now, remember, it stops at fluorine. We don't count our who? Noble gases. Okay. We see this? We feel good about this? We feel great. Awesome. All right, exercise 8. Ionization energy is our favorite. Okay. The first ionization energy for phosphorus is 1,060 kilojoules per mole, and the first ionization energy for sulfur is 1,005 kilojoules per mole. Why? Okay. So let me tell you what I would do if I was on an AP exam. This was me. Okay, and I'm taking the exam. I look at my periodic table and I say, okay, well, phosphorus and sulfur are beside each other or going up and down? Beside. So which argument am I going to use for this? The ZEF, the effective nuclear charge. So I say, okay, well, sulfur has a greater effective nuclear charge than phosphorus, which means sulfur's nucleus, and I'm shorthanding this, you wouldn't shorthand this if you were on the AP exam, okay? Which means sulfur's nucleus is more positive, which means the electrons are more attracted to the nucleus, which means the ionization energy should be greater for sulfur, right? But then what do I notice about the data that they gave me? The ionization energy for sulfur is actually lower than the ionization energy for phosphorus. Does that match what we have learned so far? No. So that means this must be one of the exceptions that we talk about, which means if I can't remember exactly what it is, what do I need to do? I need to draw it out. Okay? So I draw it out. And I say, all right, sulfur is 1s2, up, down. Well, let's just do its noble gas, or I'm going to be drawing this forever. Okay? So sulfur is neon, three S2, up, down, and then 3P, 1, 2, 3, 4. Phosphorus is neon, 3S2, 3P, 1, 2, 3. Why is it easier to remove this electron from sulfur versus this electron from phosphorus? There you go. Okay? This right here, sulfur gets rid of this electron easier than phosphorus does because sulfur is trying to what?
Minimize electron.
There you go. Minimize the electron-electron repulsion. Okay, why do we want to minimize electron-electron repulsion? There we go, because we want to lower the energy so we become more stable. So that's why sulfur is willing to part with this electron easier than phosphorus is willing to part with this one, even though sulfur has a higher effective nuclear charge. Make sense?
So
Okay.
if we wrote all the first part, would we have to like cross it out or whatever?
No. What I would do is I would always write what holds true first. Okay? Write the argument that you know to use and then say, but sulfur experiences electron-electron repulsion. So it requires less energy to remove that electron to minimize the repulsion, to lower the energy and make it more stable. Okay? Start with what you know to be true first. Okay? Then write why this is an exception to what you know to be true. Okay? Because if you'll write what you know first, even if you mess up a little bit when you're talking about the exception, they'll be more willing to believe you do know what you're talking about. Okay? Because I know what it should be, and I know it's not that, and this is why I think that it's not that. Okay? And what I'm saying is, more than likely, they're at least going to try to give you some credit for what you know. Because if you write this whole first part for me in green, then I know you know what you're talking about. Okay? So that didn't just come off from nowhere. Does that make sense? Okay? Show them what you know. All right, exercise 9. Consider atoms with the following electron configurations. And then the first thing says, identify each atom. What is 1s2, 2s2, 2p6? Neon. Okay. Whoops. Well, it's not wanting to work. There we go. Nope. Neon. Ah. There. Go there. Go there. Go there. There we go. Neon. Okay. What's 1s2, 2s2, 2p6, 3s1? Sodium. What's 1s2, 2s2, 2p6, 3s2? Magnesium.
You don't need to say it all, just say the last one.
Which atom has the largest first ionization energy? Huh? Neon. Okay. Why does neon have the largest first ionization energy? It has the highest what? Effective nuclear charge, right? Because as I go across the periodic table, what happens? My effective nuclear charge increases, okay? Which means it's going to be harder to remove an electron. Look at 9, look at 10, and then I will see y'all tomorrow.